probably is better just to get working on the assignment and ask questions. So this is the one, you guys did this as board work, right? Okay. And we were just kind of debriefing, and you had run into some difficulties, and so let's talk about how we could avoid those difficulties in the future. What should you do here? Well, for one thing, you always want to be very explicit about evaluating this expression at the upper limit of integration in brackets, right? So you can clearly see that this right here is f of 2, right? It's the antiderivative evaluated at 2 minus, in brackets, this expression evaluated at 1/2. Okay, what's this going to give us if we evaluate this at 1/2? 4 times 1/2 is 2 minus 3 over 2 times 1/2 squared. 1/2 squared is 1/4. What's 2 times 1/4? 1/2. So in the denominator, I've got a 1/2. 3 divided by 1/2 is just 6, right? So I end up getting 8 minus 3/8 minus 2 plus 6. So what's that give us? 12 minus 3/8, I guess. So 196/8 minus 3/8 is 93/8. Was that the answer? Yeah, if you just evaluate that, you get 93/8, which is the right answer. Okay? Makes sense? Where people made a mistake is they got lazy about putting the negative out in front of that whole expression and then distributing. That's just too many mental steps. You try to do that, sometimes you just make silly mistakes. Okay? The other thing you could do is we could split this into two separate expressions that we evaluate from 1/2 to 2 also. But it doesn't really help much. I mean, it's just kind of 6 of one, half dozen the other. Same thing, right? Okay, so now what about something like that? So we're trying to find the area under this piecewise function in quadrant 1. Okay, well in quadrant 1, what's that mean? That just means everything above the x-axis and to the right of the y-axis. Yes?
So can we just do it like x squared from 1?
From where?
From 0 to 3?
Yeah, exactly.
And then the other one from
Exactly.
3 to 6 and then add them here?
Exactly. It's just going to be two separate areas, isn't it? Because I'm going to have to add up the area under each of those pieces in quadrant 1 separately and then just sum the two. Anybody see that? Okay. How would you know to do that? Well, I mean, maybe we're looking at a graph. That would probably, well, you'd know to go from 0 to 3 because that's the end of the domain for the top piece of the function, right? And then how would you know to go from 3 to 6? Well, you just have to figure out where the x-intercept is of that line. Okay, but you could just look at a graph too. Okay? So that's all we're doing there. We're just doing something like the area is going to be the integral of what? X squared dx from where? 0 to 3. Everybody buy that? I buy that. Okay. Plus what's the other one going to be? Okay, and I'm going to want to put that in parentheses, right? Everybody see why I need parentheses there?
Yeah.
Okay. From. Okay, and you guys can do that. We don't even bother. I mean, that's no big deal to do that then, right? I won't even waste your time. You'll get plenty of practice on that on the assignment. Okay, this one, how would I integrate this one? What would I just have to do? Term by term, right? So what would I get from the green one? I'm going to get 18x minus that's it, 3x squared over 2. and I'm going to evaluate that whole thing.
Explain an antiderivative.
Okay. Can you explain like the power rule and stuff?
Yeah, okay, so the power rule, remind me about the power rule. What's the integral of u to the n du? U to the n plus 1 over and if it's just an antiderivative, indefinite integral, what would I have to include? Plus c. I don't include the plus c in a definite integral, though. It would just get subtracted away. Okay, how come? Because we're just playing calculus Jeopardy. I'm asking the derivative of what would give me this? Well, the derivative of that. How come? What would I do if I differentiated this? I would take the exponent out front, n plus 1, which would cancel the n plus 1, and I would subtract 1 from the exponent to get u to the n. That's why, right? We're just playing calculus Jeopardy. Okay, were you here the day, I don't think you were here the day we did, so you want to watch that video for sure.
Send me an email that I watched like the first bit and then I also.
Yeah, you got to watch it. You got to watch that one. That's all it is calculus Jeopardy. You're just trying to turn the differentiation process backwards, and you're saying, what could I differentiate to get the integrand? Okay.
But if there is none, then you have to add a constant because the derivative of any constant is just 0. So, you know what I mean? Yeah.
Right. So this one, like if we did something like this, like let's say we wanted to anti-differentiate the integral of x squared dx. Well, what is that? Plus c, because the derivative of that expression, derivative of a constant is 0.
Okay, that makes sense.
Right, so an indefinite integral is always giving you back an infinite family of curves. If I looked at, what does this really represent? It represents an infinite number of curves representing to that function plus some constant. Adding a constant to a function just offsets it vertically, right? So for all of the infinite values of c, each one of those I would get different graphs. The family of all those graphs together is what is represented by that general solution. Okay? Okay. So, and then this guy here, you guys were about to tell me this would have just been x cubed over 3 evaluated from 0 to 3. And then I would just be adding up all those values. Right? Okay? Okay, how about this one? Find the area contained by all those functions. By the functions y equals 2 cosine x plus 2, y equals x squared over 4 plus 4, and x equals pi thirds. That's a vertical line at pi thirds, right? Okay, well, the area contained by all those would be the area, would be that kind of that yellow area. Agreed? Okay. So how would I do that? Give you a hint. Here's like you all saw a bunch of SAT questions like this, right? Like if you have a
Your SAT at Stanford is a little different.
No, SAT is the same every place you take it. SAT is what you take to get into college. It's a standard test you take everywhere. It's all the same. So like let's say they wanted to know what's the shaded area here. If the radius of that circle is 5, what would you do? The shaded area. Subtract the area of the square. There you go, right? Does that make sense? Okay. So yeah, we could do that, couldn't we? Right? The area of the circle is what? area pi r squared. 25 pi, okay. And then if we wanted to calculate the area of that square, we'd have to do a little bit of calculation here, wouldn't we? We'd have to figure out, like for example, whoops, oh, what did I just do? I don't know how I did that. Like if we made a right triangle out of this, well there's, like that one right there. If that's 5, then each one of these sides would just be 5 over the square root of 2, right? And so, you ever get that by Pythagorean theorem? Okay, so then the area of the square would just be twice that distance squared, right? So it would be 2 times 5 over the square root of 2 squared, which is the same thing as 5 times the square root of 2 squared, which is just 50. Right? So it'd be pi r squared minus, or 25 pi minus 50 would be the answer. Right? And we didn't even have to go through all the specifics. The main idea here was that I was using area by subtraction. If I wanted to find the shaded area, I was going to subtract the area of the square from the area of the circle. Okay, well, how could I use that same idea in this case? If I want to find that yellow shaded area, what could I do? How could I use area by subtraction?
Find the area under the curve, like the top one from 0 to pi over 3.
So the area under the red curve from 0 to pi thirds.
And then subtract the area under the fourth.
Bingo. Everybody see that? It's just going to be the red area, which is the area under the red curve from 0 to pi thirds, minus the orange area. Leaves you with the yellow area. Everybody get that? Oh, it's the same principle. We're just using calculating area by subtraction here. Let me see here. I tell you what. Let's look at that visually, and it'll stick with you more. In fact, I'll be surprised if I don't have. I'm going to be disappointed in myself if I don't have a link to this. Oh man, I think I'm going to be very disappointed in myself. Yes, I am. Darn it. Okay. Let's build this.
Can you show us how you build it?
Yeah. It's Desmos is. You guys should just kind of mess around with Desmos a little bit. It's so good, so useful.
I had to, for some of them, like, it's the way you're on page, and some have a couple letters, like 1.5 pages. So I think the margin's like 5 inches.
Okay, so yeah, let's just build all these functions. So we get I'm going to go ahead and give them function notation. So we'll call this first one f of x equals 2 cosine x plus 2. And let's make that one orange so they all match up. Okay. We're going to graph the function. We'll call this next one, how about g of x? I probably could just call them y's, but we'll do this. Okay, and that one needs to be red. And then we've got x equals pi thirds. And there it is, right? Okay, so now let's add up the areas under these. So, oh man, do I not have one of these set up? I do. Oh yeah, I'm just going to cheat. I'm going to use this one.
That's what you're doing. You're going up, and it's going with you. Like, it's supposed to be like you actually. It's like you get right back. You're going back. My uncle. I say my uncle had like
My uncle has been coming to work on a little island like this. I got like water and the wall, like I don't know what you're talking about. No, I didn't get that.
Okay.
You and all of us would be children. I mean, I can go, but like, I'm not good at, like, I can't do big, like, I can do that too.
Okay, so this is the orange area, right? Everybody see that?
Wait, when did you do all this? Hold on, whoa, where did all these come from?
I'm just trying to cheat a little bit.
I was whoa.
There's the orange area, right? Okay. Now I'm going to build the red area. I'm going to use some stuff I already did a while ago because I didn't want to have to type all that stuff in. Okay, there's the red function, and we want to come up with the red area, and so let's do this. G,
If you're tired, you just,
G.
I think I write a lot.
Oh yeah, it worked. How about that? Look at that. Right? So if I just do this then, if I just subtract that orange area away from the red area, right? Because that's the area under the red curve from 0 to pi thirds, right? There's the line, there's the vertical line, and let's graph it. Let's graph that vertical line just so we have it. X equals pi thirds, and let's make it green so it matches our picture. There it is, right? Okay, everybody see that? There's the red area. Here's the orange area. If I subtract those away, what would be left? That little area up there. Okay, make sense? Okay, hey, I like that. That's pretty good. It worked. Leave, don't save that. I don't want to mess that up. So then all we would have to do is just that integral. Okay, here, let's do it. Let's find out what that area is. Okay, so what are we going to get? What's the red stuff going to give us when I integrate? Okay, good. That's going to give me, oh man, did it do that? Oh. You want to do that? Yeah, I bet you like that. Did I not tell you you would miss derivatives?
I missed the power roll ones.
You guys threw stuff at me when I told you derivatives are easy.
Not the ones that took a whole page.
junior year when I wasn't in this class.
You missed trig?
Yes.
I also missed trig. I wish I could go back and do trig where I was like there, you know, instead of like being wrong all that.
I wish we didn't have Jason in my class, but Jason's tracked it all over.
He wasn't in trig. He dropped. Yeah, they were in trig.
Okay, what's this one going to give us right here?
4x.
He's in the back of the room.
Yeah.
Like every day.
Okay. What's this guy give us?
Negative 2 sin x.
No. What's the, okay, what's the, remember, you got to play Calculus Jeopardy. This one's a little confusing at first.
Just sin x.
Yes.
Because it's not negative.
Right, the derivative of cosine is negative sine, but the integral of cosine is positive sine because we're playing Calculus Jeopardy. The derivative of what is cosine x? Positive sine x, right? Okay. So then we get this part is giving us 2 sine x, but it's being subtracted, okay? And then finally, what about this one? 2x that's also being subtracted. Okay, and all that stuff is being evaluated from 0 to pi thirds. But we could combine a couple things, couldn't we? Right, we could combine those two things. And so we end up with x cubed over 12 plus 2x minus 2 sine x from 0 to pi thirds. So if we evaluate that whole thing at pi thirds, we're going to get something kind of ugly, right? I'm going to get, at pi thirds, that's going to give me pi cubed over, yikes, 27 times 12. Somebody tell me, what's 27? Well, we can figure that out. What's 25 times 12? What's 25 times 12? 300. So if 25 times 12 is 300, what's 27 times 12?
324.
That's it, 324. Okay, so we get pi cubed over 324 plus what's that going to give me? 2 pi over 3. And then what's the sine of pi thirds?
Oh gosh, I don't remember that off the top of my head anymore. Wait, let me draw my triangle on my desk.
Remember the hand trick I showed you?
No, I don't.
Oh, the hand trick, right? So if you go pi thirds, there's 0, pi 6, pi fourths, pi thirds, right? You're going to get, the sine is going to be square root of 3 over 2. Oh, hold it. Yeah, that's right. Right? It's, remember, this is the angle. It's an ordered pair. The cosine is going to be the square root of that number divided by 2. So it's 1/2. The y-coordinate, so there's my comma, the y-coordinate is going to be the square root of 3 over 2. Okay? Right? So I get square root of 3 over 2 times 2 is square root of 3 minus square root of 3. So that's all the stuff I get when I evaluate it at pi thirds. What am I going to get when I evaluate it at 0? 0, exactly. So that's my answer right there. Whatever that is, that's my answer. Okay? Just some number. Okay, last one. How could you use technology to do this one? Use technology to find the total area between the x-axis and y equals that function on the interval from -2 to 2. And let's say we can find it, just approximate it as a decimal, rounded to 3 places. How could you do that? How could I do it on Desmos? So what do I do?
Take the integral of
Good.
that
Integral
from negative 2
to 2. Okay.
but does it have symmetry?
Okay. Does not, does it? But there's some parts of it that do, right? Okay, but I'll tell you what, let's do first. Before we graph this thing, let's just graph the function. So there's my function. If I'm going to find the area from negative 2 to 2, I'm just looking for that area underneath the x-axis there and above the x-axis there. Everybody see that? Okay. So my question to you is then, the question is actually, if I just say find the area, it's a little bit ambiguous because they could be asking one of two things. They could be asking us to just calculate the integral. Let's try that. If I just calculate the integral of x squared plus 2x minus 3, I get that. Okay, there's some cancellation there though, right? Okay, what if they wanted us to calculate total area? They don't want us to just calculate accumulated area. What if they want us to calculate the total amount of area such that if we cut out this shape, so I've got that little lobe right down there and then that triangular piece shape up there, what would be the area of the triangular, of the cardboard cutouts? What would I do there? Any ideas? We'll talk more about this tomorrow, but how could I do that? Yeah, so now I'm saying, what if we wanted to calculate the area from negative 2 to 1? Okay, if I do that, if I take this whole thing I just did up here, if I calculate the area under that curve from negative 2 to 1, is it going to be positive or negative? It's going to be negative, right? It's negative 9, okay? What would happen if I calculate the area, here, let's put that in our, right, there's that x-intercept, okay? What if I calculate the area of our function from 1 to 2? Can anybody tell me what I'm going to get? I'll bet you money I get 7/3.
How much money you want?
How did I know?
I don't know.
Well, I could look at those three numbers and they must go together. If the accumulated area with cancellation,
27/3, and you knew you had to get to 20, so you just 7/3.
exactly, right? How much of that area had to cancel, right? I had to have canceled out 7/3 of that to get to that, right? Everybody see that? Because this top integral that we calculated is including cancellation, right? Like I could have, what if I had made the right limit of integration just a little bit bigger? Well, eventually that positive area would have exactly canceled out the negative area and would have gotten 0, right? Because of cancellation. We had some cancellation, but what we're trying to do when we calculate total area is calculate all area as positive, area above the x-axis and below the x-axis. Calculate everything as positive area. So we can see what the, what's the total amount of area regardless of sign. And so we needed to find out, well, where's the x-intercept of that blue function? So we would know to catch only the negative area and make it positive, right? And then we'll take the area that was previously positive and just leave it positive and add those two up. Okay, and so if we did that, that would be like taking an absolute value of those areas that were either exclusively negative or exclusively positive. Like, what's going to happen if I take this whole thing and I just take an absolute value of it? Well, now it becomes positive 9. That becomes positive 7/3. Well, okay, if I just add up all that area as positive, then I'll take that piece plus that piece. I bet it's 27/3. Oh, what the heck, 34/3. How do we get 34?
You need to add the absolute value of the top one to 7/3.
Did I
win money?
Did I mess that up? Oh, yeah, I did. I did. It should be 34/3, right? Because there was a total, we canceled a total of 14/3, right? To get negative 20/3, right? We canceled 7/3 of the negative area and 7/3 of the positive area. So it should have been 34/3. Yeah, that's right. The total area. Okay? Right? So how would we do that without a graph? This is the stuff we're going to talk about tomorrow. How do we do that without a graph? Well, we'd have to figure out where are the x-intercepts of this function. So we'd said x squared plus 2x minus 3 equal to 0. Yeah, we'd factor that, and what would we get? What are the magic numbers here? Yeah, plus 3 minus 1. Good. So we don't have to use quadratic formula or something, right? We can just do this way. And we're going to get solutions x equals negative 3 or x equals 1. Those are my x-intercepts. Okay, we don't care about the negative 3 one, though, because that's outside of our domain. We only want to calculate total area from negative 2 to 2, right? So then we're going to have to, this one is irrelevant, but this one is important. Okay? So then we're going to have to break this up into 3 intervals. We're going to have to, or 2 intervals, right? We're going to have to take the interval from negative 2 to 1 and the interval from 1 to positive 2 and add up the areas on those 2 intervals, right? Okay, so that's going to give us the integral of, let's just call this thing f of x. So I have to write it every time. Integral of f of x from negative 2 to 1 plus the integral of that function f of x from 1 to 2. But if I did that, this would give me a negative value because it turns out that we saw the graph, the function is below the x-axis from negative 1 to 1, and it crosses over and is above the x-axis from 1 to 2. So to ensure that I'm always adding up positive area, what would I do? Absolute value. I take absolute values of both of those. The absolute value of that area plus the absolute value of that area. As a general strategy then, all I have to do is find all of the interior x-intercepts and integrate about in intervals that are broken up by those x-intercepts, taking the absolute value of each of the definite integrals that we calculate, right? Each area that we calculate, I just need to make it positive. Okay, give me 1 to 5 on that. Does that make sense on that strategy? Sort of, kind of, maybe? Okay? That's what we'll talk about tomorrow. I was just giving you a little heads up for tomorrow. So we're going to talk about total area versus, like, gross area versus net area, accumulated area versus total area. Okay? Okay, it will be taped.